Hey guys, what's up? This is Madan here, and I've come with another video from haloalkanes and haloarenes, and this is like going to be the second last topic, and I'm very hopeful to complete the whole chapter today, possibly if I can. So what topic I'm about to take you through is I've already mentioned a little bit of that because I thought the recording was all going on, but it wasn't happening. So I have to repeat back everything I've just mentioned right here. So what this whole topic is, let me introduce you. All the haloarenes, you have to understand that all the haloarenes are extremely less reactive with any nucleophile. So nucleophilic substitution reaction for the haloarenes are not easy, or I should say they are not easy to go. So they are extremely less reactive towards the nucleophile, right? So that's what I mentioned the topic here, nucleophilic substitution reaction of haloarenes, which I have repeated that all the haloarenes are extremely less reactive towards nucleophilic substitution reaction, right? And it's because of the following four reasons. All the nucleophilic reaction with haloarenes are not possible because of these four reasons. What these four reasons are, let me name them and then I will explain you one by one. The first one is because all the haloarenes exhibit, I'm talking about the haloarenes. So all the haloarenes exhibit plus R effect. What this plus R is, I'm coming to that. They have sp2 hybridization, they have instability in their phenyl cation, and finally any two reactants have repulsive interaction naturally because they have electron. So the fourth one is not that significant, but first one and first and second one going to be very, very significant right here. So let me explain, one by one, all of them. So the first one, is that haloarenes exhibit plus R effect, right? This is also something from 11th class, but because it's coming up right here, so I have to, I have to make you go through. So suppose this is a aryl halide here, right? And place a halogen here, any halogen you can. So what you do know that halogens have 6 electrons right here, and all these positions are occupied by hydrogen. You do know that. So what happened here, being halogen electron rich, a pair of electrons shift to the adjacent sigma bond. But because the sigma bond because the number of electrons around this particular carbon increases from 8 to 10, so what happened, the adjacent pi bond electrons shift over the next carbon. So because of this, what changes is coming up here? What changes is coming up here? This will become a double bond here with halogen, only 2 pair of electron with a positive charge, and there a pair of electron is coming up with a negative charge. So this is what the thing is. There you have already your double bond, there you have already your double bond. So now what you see that due to electronic mobility, the bond between carbon and halogen acquiring a double bond character. So because of presence of the double bond, because of the presence of partial double bond character, this bond becomes very, very difficult to break. And if this bond does not break, of course, no nucleophile will be able to substitute the halogen. I hope you have understand what I'm trying to say. Because of the partial double bond character right here, due to resonance, this halogen and carbon bond will become difficult to break, and that's why nucleophilic substitution reaction with haloarene does not take place. But let me complete all of these steps here so that you also understand what plus R effect is. What happened in the next step? This pair of electrons shift there, and from there it undergo resonating like that. So what you have next is, you have now a double bond right here, a double bond right here, a halogen with a positive charge and 2 pair of electron. This double bond is still there, have nothing been done here. Now there is the pair of electron and a negative charge. So what happened in the next step? This goes up to here and this pi bond shift next there. So in that case, what will happen? This is what the next structure is coming out to be. So this is what the next structure is coming out to be. There is negative charge, there is a double bond already, there is another double bond here, halogen with a positive charge, lone pair, and now the double bond is here. So in the last step, what will happen? This will go up here and this will be shifting here, right there. So because of this, the final structure is coming in existence, and that is, there will be a double bond, there is another double bond here, and there is one, two, sorry, there is a double bond here and there is another double bond here, right? So there is halogen with no charge. So I hope you have understand that these are, they represent to, let me tell you, they represent to plus R effect. They represent to plus R effect called resonance effect. These are called resonance effect here. So let me come back to the topic again and explain you. So this is plus resonance effect. Okay, I was saying that all the haloarenes are not reactive towards any nucleophile because of the four reasons. The first reason I have made you go through, and the first reason is that, because of presence of halogen on the benzene, it undergo resonance, development, and during the resonance development, what happens, the bond between carbon and halogen acquire a double bond, and because of presence of double bond there, the bond becomes difficult to break, and if the bond does not break, the substitution reaction will not take place. So that was the first one. Next one is coming out is sp2 hybridization here. So sp2 hybridization. So what this is, in haloalkane and in haloarene, we'll be comparing. This is your haloalkane, and there let's take a haloalkane here. So what you see out here, that should be right like this. So the hybridization of this carbon is sp3, right? And the hybridization of each of these carbon is sp2, right? So what is happening here? The ratio of S and P. Here it is 1:2. Here it is 1:2, but there it is 1:3. 1:3. So this is like this is like a 33% S character, 33% H character, and sorry if I am making mistakes here, and there it is 25% S character. S character. So what is happening, S character is in this case more, and let me explain right here, because not everything you have to make a copy of that. Greater the S character in a bond, higher is the electronegativity. Higher is the electronegativity, shorter will be the bond. Shorter will be the bond, higher will be the bond enthalpy. So what I'm doing right now here, that it has high electronegativity, and hence short bond length, shorter bond, and high bond enthalpy. High bond enthalpy. I will explain it, but let me write it a bit so that you can also make a copy of that. So low electronegativity, and longer bond length, longer bond. So weak bond, so weaker bond, and low bond enthalpy. Low bond enthalpy. Let me explain here. In simple, what we see out here, that in haloarene the hybridization is sp2, in haloalkane the hybridization is sp3. There the hybridization, if you look at the hybridization, the S character is 1:2, 1:2 here, but there it is 1:3. So what we see that there are 33% S character, but there is only 25. So higher the S character, higher will be electronegativity. Higher the electronegativity, greater will be, higher the electronegativity, shorter will be a bond, stronger will be the bond, and if the bond is stronger, the bond enthalpy become higher. And if the bond, what that means in simple way, that this bond, you need to understand that this bond is very, very stronger bond as compared to this bond. So this is like, this is going to be a weak bond here. This is like a weak bond here. and there is a strong bond here. Strong bond. So that is also one of the reasons why the haloarenes do not undergo substitution reaction very easily. So that's it. Let's take you through the third one is, instability of the phenyl cation. Phenyl cation. So what this phenyl cation is, let me help you with that. Suppose if somehow the bond between halogen and carbon is broken, concentrate here. If somehow this bond is broken, then what is going to happen? It will form a phenyl cation. It will form a phenyl cation. So there will be a positive charge and halogen will come out as a negative charge. So this is your phenyl cation. This is your phenyl cation. And this phenyl cation cannot be stabilized by resonance. This cannot exhibit resonance structure. You have to understand, cannot be stabilized by resonance, and therefore it had less possibility to react. So with that, I must say, you have to understand that the phenyl cations are very unstable and they cannot be stabilized by any further development. So that's why they cannot undergo reaction with any other nucleophile. The fourth one was, make this here because that's not something, I'm going to explain. The fourth one was repulsion between haloarene and nucleophile. So this is the fourth one here. There's nothing to explain, but I would say one thing, that because any two reactants always have the electrons, and electrons are always a cause of repulsion because of similar charge. So this will also play a huge role in preventing the nucleophilic substitution reaction by any haloarene. So with this, I have completed the second last topic of the haloarene. Now the one last thing I'm still remaining, I will do that today in the next video. So I'm very sure now I will complete the chapter. So I must say, just take care of yourself and don't forget to keep coming. You have to keep coming.